Okay, this is the aerial and ground confidence percents and calculation parameters. Okay, that was a lot to say, wasn't it? Let's get rid of that right now. Okay, it sounds ominous. We don't have to look at it. What this is to show how the aerial and the ground games work together to obtain the best from both worlds. We also show how information in the scale creates our confidence percents right in here and over here. We take all of our information from the air and from the ground to come up with species, volumes, and quality of timber. We then compare these numbers to what is actually scaled in the sort yard to come up with comparison percentages, which I'm showing right here. Okay, we're going to assume that our scale number is the true number of what exists in the forest. We'll ignore the human factors, that some timber is broken up in the logging process and never gets to the sort yard, or that it is sometimes inadvertently bucked to non-optimal lengths and so on. For now, I'm going to call the scale numbers the true number. Okay, for example, let's look at stems per hectare. My pixel algorithmic says that we will be within 80% of whatever we get here of the true number from the scale. Okay, it says here that if I do one plot, it says that I will be within 55% of the number of this scale. Well, where did I come up with these numbers? Well, to start with, a person has no choice but to derive these numbers from his own experience or from the experience of other people, or even if you have experience, to talk with other people. It's a little bit like Euclid's axioms. You know, when his axioms, he didn't know if they were true or not, but like all triangles have 180 degrees, the shortest distance between any two points is a straight line, etc. He developed these axioms based on his common sense and observation, which is what we have to do to begin with now. But over time, we're going to go from that, and we're going to actually work these numbers with what we see on the scale, and that's really going to be very important. Okay, we learned that from our pixel algorithm here that we have 80%, and one plot is 55%, three plots is 75%. Or we may learn something entirely different when we start working this with the scale. Okay, whatever we learn is the numeric percent that we will place here in these spots. Okay, it could be asked how one derives a one, two, or three plot average from many plots actually recorded within a certain forest type. Well, there's a bit of iterative math here. We might find some formulas here. What have we got here? Formula descriptions. To create a one plot average from many plots, simply add each plots together, percentages together, and divide by the number of plots. That one's simple. For a two plot average from many plots, each plot must be averaged to each other separate plot individually. Then these averages are summed and averaged. Okay, sounds a little complicated. It's not. It's just iterative. The same method works for three, four, or more plots average percents. The computer actually does all of the work there. Okay, an example of that would be this algorithm here, which is a simple basic algorithm that does the iterations for calculating what these percents will be for a 1, 2, 3, 4, 5 plot or more plots. What percent we're going to get likelihood of becoming within the true number from two plots, but we're going to base that on many plots. So anyway, there's a bit of work to do there, but the computer does most of it. And we can build these percents from many different blocks, okay, surveyed, logged, and scaled as a history to continuously refine how close our forest measurements come to what is actually scaled. In other words, these numbers are continuously refined over time. So how does the computer work the aerial data with the ground data? Okay, it's called weighted averaging. Okay, for example, right here we've got 80% confidence in our pixel algorithms, and over here, if we put in four plots, we've got 85%. Well, how do we compare those two? Okay, well, that's weighted averaging, and I'll just put the number down. It means that since we have a higher percentage confidence in this, whatever number we get here, than what we get here, we're going to put this at 52%. This number, whatever we get here for four plots, is going to be worth 52%. And whatever number we get here from our pixel algorithm, it's going to be worth 48%. That's just called weighted averaging. Okay, we could also do it a different way. We could say, what about 80% with one plot, 55%? Okay, well, that's just a number thing. That means we've got 59% we're going to weight this according to 59%. This number is going to be worth 59%, and the number we get here is only going to be worth 41% when we average them together. That's just called weighted averaging. It's no big deal, but that's how we make sure that things are bouncing back and forth and working as best that they possibly can. Okay, these numbers might look kind of precise, like 95% confidence right here for 5 plots. And we might think, well, what's the likelihood you're going to get that? But actually, there's nothing weird about it. The plots we do at Precision Analytics are not the same as typical ministry plots where you try and get maybe 4 trees at an 18 bath or whatever. Our plots include 3 extremely important parameters. Let's see if I can find those parameters somewhere over here. Right here, okay? In order to get high confidence percent statistically accurate, we do 3 things. One is a 15-meter fixed radius plots using a LiDAR rangefinder, which typically includes about 20 trees per plot. Okay, with these large tree numbers, the variation is smoothed out considerably, and the plot's similarity to the surround forest is greatly increased. Okay, that's really a good way of doing it. Okay, tight homogeneous phototyping. This is where the aerial and ground games really work together impeccably. By creating tight, up-to-date, homogeneous polygons, we keep our variations to an absolute minimum. This is really important. This isn't down here. Confidence in phototyping to create tight, homogeneous polygons, 100%. We have to have really good aerial data and really interpret it well in order for these numbers to be high like they are. If this is done poorly, then this is done poorly. So this is a perfect example of how the aerial and the ground game work together in a complementary fashion in unison. Okay, now let's try. Our third one is mostly random plots. I like random plots because they make sense, but which occasionally move to representative plots. If a plot falls into a very unrepresentative tiny area, we're going to move it. Keep in mind this should seldom happen when the phototyping is tight. If this happens very often, then you know your phototyping is bad and it needs to be redone. Okay, with these 3 things, our accuracy is maximized. Some people are going to say, I know, I can just hear it already, that, oh, to put in a 15-meter fixed radius plot would take forever. To grab 20 trees would take forever. Well, the answer to that is no. It is very, very fast and efficient. Okay, this is where we should keep something else really well in mind. This concept is that procedures and methodologies are every bit as important as technologies. Sometimes it can take years to develop a procedure. And when developed, it's worth a lot. Okay, this is where I would like to run this comparison. We've spoken about the importance of working our aerial game and our ground game together in complementary cohesion. It is no less important to do the same with technology and methodology. These both need to always be working optimally and in support of each other. Okay, now technology. It's also important to remember that just because something is new doesn't mean it's better. However, I think new things should be tried, not just dismissed. Some people are great at technology, but their methodologies are useless. I know people that if their iPad stopped working, I doubt they could navigate their way out of the bush at night. Certainly not with any precision at all. And methodologies which take years to develop usually take a lot of out-of-the-box thinking. I know people with great methodologies but could incorporate some new technology into the mix. Remember, it wasn't that long ago that GPS was a new technology. So I say we use the technology, we use it wisely along with the methodology, and really get the best of both worlds. And they bounce back and forth in optimal fashion, just like our aerial and our ground game. The important thing is balance and optimization. Okay, let's talk a little bit about a red, dead, and blowdown, because we can see right now that our confidence in coming to the true number on the scale is very low with our plots. Now it's extremely high with the aerial game, because we can look down, we can see the red, dead, and blowdown trees, and we can just manually count them. We don't know anything about their grades, what kind of shapes they're in, but boy, when it comes to stems per hectare on red, dead, and blowdown, I have 95% confidence that we're going to hit bang on with the scale. Assuming that the scale takes most of these red, dead, and blowdown, doesn't leave them in the bush for waste. Anyway, over here with plots, you might ask, well, why do I have such low percentages? Or I have high percentages here, I have low here. And that's the problems involve the patchy nature of these trees. You're going along, all of a sudden you have blowdown, then you don't. You got dead trees, patches, then you don't. So there's so much variation in here that it's hard to have any confidence that we're going to get to the number we want on the scale with ground plots. But I have extreme confidence that we're going to do it from the air. So anyway, even if we have type homogeneous polygons, it's not going to be very good with our ground plots just because of the nature of the beast. Okay, let's talk about species per hectare. Oh my goodness, this is a brand new thing. Okay, we know that species differentiation is very important, and we will see in a minute why stems per hectare is also. Because these two work together, stems per hectare and species together work together, and we'll see why in a minute. At this time, my confidence is that our species percent numbers from algorithmic processing is 70%. I'll get into exactly why in a second. You might not think that's very good, but it actually is pretty good. And it's better than using the 3D count based on crown shape, okay, variation. And this is also very manual, very labor intensive, takes a lot of time. This one's virtually instantaneous and comes up with better numbers, okay? But still, the number is what it is. So let's divert a minute and talk about how we're getting our pixel algorithmic based upon color separations. Okay, here we go. Okay, let's go over here to somewhere where we've got a picture that we've taken from the air, right here. Here's a good picture. Okay, now we'll notice a couple things. This tree right here is a Douglas fir. This one right here is a hemlock. Okay, let's just zoom in a little bit. See if we see any differences. We can see for one thing that the fir is crowding the hemlock out from two sides. This is also a fir, so it's being crowded out because it's shorter. Okay, but we get in there and we start noticing things. We'll notice that we can't quite see the needles because the resolution isn't that high. But we can notice that we're looking at a lot of pea green colors, a lot of tan colors and things in here. Whereas in the fir tree, we're not. We're looking at more deep, lush greens, rich greens, a little bit of bluishness down in here. But we're looking at different colors of green, along with some pea green thrown into it as well, because it's got that, and even some major stuff right there. But still, within the hemlock, we got very much tans and light greens. Okay, so what does that mean? That means that when we put this together, right there, back off a little bit here and get this into the thing. When we average all of the colors from our fir tree here together, we get that color. Okay, when we average all of the hemlock colors in this tree here, we get that color. You might look at that and say, well, that's not bad. That's quite a bit of difference in color between the two species of trees. That's quite a bit of difference. Okay, we'll get back to this picture in a minute. But right now, let's go to what this all means. Okay, right now, we've got our two colors. We've got Douglas fir right here. When this is our archetypal Douglas fir tree is on the scale, on the intensity level scale of red, green, and blue. Its intensity level, it shows up in red right there, but its red is 138, green 170, blue 98. Okay, that's what it is, whereas the hemlock is 191, 195, and 115, and that creates this color. So these three numbers create this color. Okay, the problem is if I try telling the computer to look for these two colors, which is a fir tree and this is a hemlock tree, it's only going to come up with a handful of pixels because there's just not many that are going to hit right on that perfect. We have we have a range. Like in the red range, we have a whole range here, and I'll show it right up top here. The range is on Douglas fir is starting from here, going to lighter to right there. Okay. In the western hemlock, it goes from there, and then it goes to there, quite tan right over here. So there won't be a lot of pixels in this really light tan, but there will be some. This is our range. Okay, and I've got it done in numbers. It's done by the numbers in the range here. Okay, now let's talk a little bit about the red, green, and blues. Intensity levels of red between fir. Okay, if you look at this, we've got an intensity level, and we're saying that all of our fir trees have red in this intensity level of the red spectrum. Hemlock has it all here. And one thing I really like about this is I like the fact that they don't even overlap. Isn't that neat? No overlapping. Okay. In the green levels, okay, we've got the same thing. This is our fir. This is our hemlock. And if we wanted to grab this right up here and put it right up there, we'd see there's a little bit of overlap, but, not really too much. So, that's pretty good. We get down in here into blue. And we think, oh my, there's lots of overlap. It really is. In the blue part of the spectrum, we've got a whole lot of overlap. And that creates some problems. And down here in the combined levels, I've got everything combined. Red, green, and blue combined in Forget the fact that this is purple or violet. It has nothing to do with ultraviolet. It's just another color I had to show out that wasn't red, green, or blue, so I can tell you the combined levels. When we combine all three, here's what we get. The fir covers this range at this bell curve, and the hemlock covers this range at this curve. So if we combine them both together, here's what we get. Now you notice we got a chunk of overlap here, quite a bit of overlap. I've actually calculated the numbers on this overlap, and it ends up being 30% overlap. Between our fir and our hemlock, we have a total of, when you add up all the colors, there's a 30% overlap. So what does that mean? Okay, well, that means something right here. It means that we have a bit of a problem. Okay, right here's our fir. Right here's our hemlock. Okay, right here's our fir, and here's the 30% overlap. Okay, how do we deal with that? Well, one way we could deal with it is we could say, we'll ignore the overlap, and we'll take all of our fir, the stuff that we know is fir, and all the stuff we know is hemlock, and we'll take a percentage of fir, a percentage of hemlock, whatever that is, and we'll have a, this is what the pixel said we had, okay? So if we had 100 stems per hectare, this is where stems per hectare comes in really valuable and important, is that if we had 100 stems per hectare, that means 68 of them is fir, 32 are hemlock. Okay, but I happen to know, even though these trees are being overshadowed, there's about 6%, say, of cedar in there. So let's throw in a 6. Okay, we can't just throw in a 6 without taking away 3 from each of these. So we'll take this down to 65. We'll take this down to 29. Except now we're dealing with our problem again, okay? We're dealing with the fact that our hemlock is being overshadowed by our fir, which we see right in here. I figure about 20% of this hemlock tree is being overshadowed by fir branches crowding in from the side, and about 10% over here. So about 30% of our hemlock tree is not even showing up. We can't even see it. It's being overtopped. So you might say, okay, well, we need to put a little bit more of a percentage on the hemlock and take it away from the fir. So let's just do that. Let's take away 5 points from the fir. So we'll call that 60. And let's give that 5 points to the hemlock, which should turn that into 34. Okay, I hope things worked right there. That looks about right. Okay, now we've got it. Now we've got different percentages that we're working with. Okay. Now, we can do this one of two ways. We can ignore the intermediates, okay, or we can just take the intermediates at different levels. We could say, okay, the hemlock, instead of cutting it right in half and taking half of the intermediates go to hemlock and half go to fir, we can say, no, we need more of that to go to the hemlock because it's being overshadowed. So we can take 3/4, 2/3, whatever. We can change these numbers is what I'm saying. We can actually change these numbers. But in doing so, we're now involving ourselves in a bunch of guesswork. And of course, I don't like to guess. I don't like to do much guesswork. I don't like to do it at all. This is kind of interesting how this worked out in this particular case, because I've analyzed that we're 30% intermediate. 70% of our entire thing right here is actually not overlapping. Only 30% is overlapping, 70% is not overlapping. It's kind of handy actually when you look at that and you think, my confidence in my algorithmic processing is 70%. Wonder if that's a coincidence. Now realize that this 70% is actually going to be compared to the scale. We're going to find out how close this number is to the scale. And is it going to be 70%? Well, it will be if we do things right. If we do things wrong, it can be less. But I would like to do things better. I would like to get that higher than 70%, if at all possible. In order to do that, we have to have less. Intermediate pixels here. Okay, less spillover. We need this to be less. I'd like it to be like 10% or something like that, not 30%. We'd be way better off if we get this down to like 10%. And then we're all of a sudden, we're way more sure of our numbers, and also get our cedar to start showing up a little more since it's down so low that we can't hardly see it. Okay, so how might we do that? Now we can talk a bit about the pixel ranges here. Now I think we've about maxed out what we can do with the RGB range. Forget ultraviolet because that's getting into a different ballpark. But the RGB range, I think we've sort of maxed out what we can do here. Is there any way that we could possibly increase this to like 10% instead of 30% overlap? Well, I think there's a solution, but I haven't done it yet. I've kind of gotten my feet wet a little bit, gotten into the shallow water of it, but I'm thinking the next best thing is multispectral, which is 20 nanometer step resolution, Hyperspectral is 1 nanometer, which I think is not necessary for the near infrared. If we start working the near infrared, which is 740 to 1400 nanometers, a nanometer is 1 billionth of a meter. Okay, we work the RGB range, which is 380 to 740. That's what we've been working. That's what we're doing. When you get above 740 up to 1400 nanometers, we're in the near infrared. We're into light that we can't see, but cameras can still pick it up and then artificially show us what's there. And I'm thinking that we might get some better pixel separation. We'll increase this from 30%. We might even be able to get it to 90%. Wouldn't that be something? That's the next. That's on the agenda. Okay, we're going to increase that number, and we'll know when it's increased because this 70% will start working with the scale a lot better. Okay, well, what's there to say now about speed, tree size, and gross volume? Okay, there's stuff to be said there. We get without LiDAR, we got basically nothing. I call it 5%, but that's essentially nothing. With LiDAR, we have some heights. That's all we've got, but we've got some heights. Well, that's better than nothing, so that gives us a 20% chance, I figure, of getting within the true scale, or the true number. Okay, with our ground plots, this is where we get really well. We got 55% with one plot, and we move on up. By the time we got 5 plots, I think we're over 90%. Now remember, that's assuming 2 things. That's assuming 3 things that we already talked about. That's assuming extremely tight polygons, which have very little variation within them. It includes big plots where you get about 20 trees, so you're really smoothing things out in that department, and you use representative plots. You don't let any zero plots or things like that get in there should that happen. So between those 3 things, these numbers can be really high. And when you get up to 95%, I'm saying it's good ahead. Run the variation on your plots and see if you get within 95%, which is 2 segments of confidence. Run the variation when you get up to 5 or more. It doesn't tell you how things are going to compare with the scale, but it does tell you how they compare with each other on the variation. And so that's an important number to get. Okay, next let's go down to tree quality, grade, and net volume. Well, okay, the aerial game gives us 0. Okay, it doesn't do it. But here's where we get the ground game really gives us these numbers. It gives us the grades, the qualities, and the volumes. We get that from the ground, okay? And then we plug that in, and I'll show that how that's done in a minute here. But from our aerial game, remember, our aerial game, we get 100%. Its value is 100% on creating tight polygons, 0% on the ground. As far as estimating erosion, mass wasting, burns, and so forth, that's 100%, 0% on the ground. These things really work to help us get better numbers on the ground, and our ground numbers really help us get better numbers in our air game, and all of that is the proof is what we get in the scale. Okay, we want to make sure that when we give numbers, what's in the forest, it needs to be very close to what it ends up at the mill. That's the entire goal, right there. Okay. In fact, right now we could even have a look at some charts and things right here.